Suppose you build a test for a rare disease, one that shows up in just 5 people out of 100. You want one number for how good your test is, and the obvious one is accuracy. Out of everyone, how often were we right? Now here's a lazy model that never even looks at the patient. It says, healthy to everyone. Right about all 95 healthy people, wrong about only 5. So its accuracy is 95%. That sounds superb. But look what it did. It missed every single sick patient. All 5. A test that catches none of the people it exists to catch is worthless, whatever the accuracy says. Accuracy hides which kind of mistakes we make. To see them, we need a better tool. Here is that better tool, the confusion matrix. Every prediction is positive or negative, and the truth is also one of the two. Cross them, and exactly 4 things can happen. We lay them out in a 2 by 2 grid. The columns are what the model predicted. Positive left, negative right. The rows are the ground truth. A row tells you the real class. A column tells you the model's call. Keep that straight. It's the one thing people flip. A true positive. Predicted positive. And it really was. Think of a spam filter. Junk mail correctly sent to the spam folder. A false positive. We shouted positive, but the truth was negative. A real email from a friend, wrongly dumped in spam. A false alarm. A false negative. We said negative, but it was actually positive. A spam email that sneaks into your inbox. A miss. And a true negative. Predicted negative and correct. A genuine email safe in your inbox. 2 of these are right, the green diagonal. 2 are wrong in different ways. Let's put real numbers in. Picture 200 patients tested for a disease, with half the disease as our positive class. The model gets 50 true positives, 30 false positives, 10 false negatives, and 110 true negatives. First, always check the total. Add all 4 cells, 50, 30, 10, 110. That's 200, exactly our number of patients. The matrix accounts for every one. Now the metrics. Accuracy is the correct diagonal over the total true positives plus true negatives over n. 50 plus 110 over 200.80. 80% correct overall. Precision asks a sharper question. Of everything we flagged positive, how much really was? That's the left column. True positives over true positives plus false positives. 50 of the 80 we flagged. 0.625. Low precision means we're crying wolf. Lots of false alarms. Recall flips to the truth. Of all the patients who actually had the disease, how many did we catch? That's the top row. True positives over true positives plus false negatives. 50 of 60 real cases. About 0.833. Low recall means we're missing real cases. You'll also hear recall called sensitivity or the true positive rate. Same formula, same idea. Precision and recall pull in opposite directions, so we often want one number that balances them. A plain average won't do. 90 and 10 average to 50, which looks mediocre rather than broken. We want a score that punishes that imbalance. The answer is the F1 score, the harmonic mean of precision and recall. 2 times precision times recall, over precision plus recall. The harmonic mean leans toward the smaller of the two. So if either one tanks, F1 tanks with it. Plug in our numbers. Precision 0.625, recall 0.833, and F1 comes out about 0.714. Notice it sits between the two, pulled toward the smaller precision. Exactly what we wanted. 2 more. About the negatives. We'll need them for the rock curve shortly. Specificity, the true negative rate, is how well we handle the healthy true negatives over all actual negatives. 110 over 140, about 0.786. Its mirror image is the false positive rate. Of all the actual negatives, how many did we wrongly flag? 30 over 140, about 0.214. And these two always add to 1. False positive rate is simply 1 minus specificity. Let's pull it together on one screen. The same 50, 30, 10, 110. Read the matrix once, then read off every metric. This is the mechanical routine to run every time. Accuracy. The full diagonal, 80%. Precision. The flagged positive column, 0.625. Recall. The actual positive row, about 0.833. And F1, the harmonic mean, about 0.714. One honest reading. 80% accuracy sounds fine, but recall of 83% means 1 in 6 real cases still slips past. And precision of 62% means a chunk of our alarms are false. Accuracy alone hid both. The matrix showed them. Where do these counts come from? A classifier rarely gives a flat yes or no. It gives a score, a probability that something is positive. To turn a score into a decision, we pick a cutoff, a threshold. Above the line, call it positive. Below, negative. The default is 1/2, but that line is a choice. Here are the model scores. Green dots are the truly positive cases. Rose dots the truly negative. A good model pushes greens toward 1 and roses toward 0. But they overlap in the middle. And that overlap is where the threshold matters. Put the threshold at 1/2 and read off precision and recall. Now watch as I slide it. Push it high. We only shout positive when we are very sure. Precision climbs because almost everything we flag is truly positive. But recall falls. We're letting cautious real cases slip by. Now drag it the other way. Low. We flag almost everything as positive. Recall shoots up. We catch nearly every real case. But precision collapses because we're flagging piles of negatives too. Raise the threshold, precision up, and recall down. Lower it, the reverse. You almost never maximize both at once. Which way you lean depends on the cost of each mistake. When a miss is deadly, a disease, fraud favor, high recall and accept some false alarms. When false alarms are expensive, flagging good emails as spam, favor high precision. Rather than commit to one threshold, we can sweep every threshold and plot the result. That gives the ROC curve, the receiver operating characteristic. On the bottom, the false positive rate. Up the side, the true positive rate, which is just recall. Every threshold gives 1 point on this square. The dash diagonal is a coin flip, a model with no skill at all, where the true positive rate never beats the false positive rate. A model with real skill bows toward the top left corner. High true positive rate while the false positive rate is still low. As we sweep the threshold from strict to lenient, we trace this whole curve. Each point is one threshold's confusion matrix. The single summary number is the area under this curve, the AUC. An area of 1/2 is that random diagonal. An area of 1 is a perfect model that ranks every positive above every negative. Bigger is better. It captures ranking quality across all thresholds at once. One caution. The ROC curve uses only the true and false positive rates. Precision never appears. On very imbalanced data, where negatives vastly outnumber positives, prefer the precision recall curve, which keeps precision front and center. Your turn. Here's a small confusion matrix: 8 true positives, 2 false positives, 4 false negatives, 6 true negatives. Pause the video right now and work out the precision and the recall yourself before I do. I'll wait. Here's the answer. Precision is the flag positive column. True positives over true positives plus false positives. 8 over 8 plus 2, which is 8 tenths. 0.80. Recall is the actual positive row. True positives over true positives plus false negatives. 8 over 8 plus 4, 8 twelfths, about 0.667. If you got 0.8 and 0.67, you've genuinely got this. Trap 1. The one we opened with, on imbalanced data, accuracy lies. 95% can mean you caught nothing. When a class is rare, trust precision, recall, and F1 instead. Trap 2. Swapping the denominators. Precision divides by what you predicted positive, the column. Recall by what was actually positive, the row. Condition on the prediction or on the truth. Trap 3. Expecting both high at once. They trade off through the threshold. Push one up and the other slides down. Choose which mistake you can least afford. Trap 4. Reading the matrix sideways. A row is the actual class, a column the prediction, but some tables flip it. Read the labels before you trust a cell. And trap 5. AUC is not accuracy. It's the area under the ROC curve, ranking quality across all thresholds. Point 5 is a coin flip. Near 1 is excellent. Let's lock it in. Start from the confusion matrix, TP, FP, FN, TN, and check the total. Accuracy is the correct diagonal over N. Precision is true positives over everything you flagged, positive. The cost of false alarms. Recall, also called sensitivity or TPR, is true positives over everything actually positive. The cost of misses. F1 is the harmonic mean of the two, a balanced score that punishes any imbalance between them. And the ROC curve plots true against false positive rate as the threshold sweeps, with EUC summing it up in one number. Fix your positive class, read the 4 counts, apply the formulas, and these metrics will never confuse you again.